Hello, fellows who come to learn math from me who probably don't exist because nobody watches my video anyways. But if you do exist, this video is about limit and continuity. So, as some people who learns math just like you guys, I know you must have a question. Why do we need to learn this thing? What is the limit? Like, why do we need it? Well, for you guys to want to learn about the limits, we need to find something that we can use the idea of limiting. That is an example. Let's say that we have a dinosaur mother. Everybody loves dinosaurs. And at the beginning of each month, the dinosaur mother lays an egg, which gives birth to a baby dinosaur. However, at the beginning of the 10th month, when the dinosaur mother is hatching an egg, as soon as the baby hatches from the egg, a meteor comes down from the sky and kills the dinosaur family. This meteor has also caused the extinction of dinosaurs. Now, let us use a function and a graph to represent the number of dinosaurs with respect to time. Before the beginning of the 10th month, the number of dinosaurs is x plus 1 because there is the mother dinosaur. However, since the beginning of the month 10, the meteor kills the entire dinosaur family, so there are 0 dinosaurs. So let's graph this. On the beginning of the 10th month, when the 11th dinosaur is coming out, the meteor lands and kills all the dinosaurs. When we're counting the number, there are already only 0 dinosaurs left, so the value of y is 0 when x equals 10. So here comes the $0 question. How many dinosaurs were killed at month 10? Now, I know you could immediately answer 11, but let's try this with math. Let's try this using our function. Your first instinct would be to find the value of y when x equals 10. When x equals 10, y equals 0. So there are 0 dinosaurs killed? Of course not. In order to solve this question, we need to use the limits. Now, this is the definition of limits. Limit is written as this: lim x to c f of x equals L. This means that f the function approaches the limit L as x approaches the value c. Notice the word approach. The value of a function means what happens at one point, and the limit of it means what happens near one point. The limit represents a value that the function infinitely approaches and does not have to be the value at a certain point. To demonstrate this, let's look at this function. This function is almost exactly the same as y equals x plus 1, with the exception that the function is undefined when x equals 1 because you cannot divide it by 0. This is represented on the graph as an empty dot at the point x equals 1. The value of y on this point is undefined, however, the limit is not. The limit represents the behavior of the function near this point. As you can see, the function approaches the value of 2 from either sides. Even if y does not equal 2 when x equals 1, y gets closer and closer to 2 as x gets closer and closer to 1. Therefore, we can see that the function's limit at x equals 1 is 2. This is how we define the limit. As you can see that the limit of function is not necessarily related to the numerical value of it. Compare the function to y equals x plus 1. Even if their values at x equals 1 are different, they behave the same at that point, so they have the same limit. Now you can write this down in your notes, or you don't really need to, because it's always better if you can memorize it inside your brain. Now let's take a look at the properties of limits, which help us calculate them. This is extremely important. However, they will be reinforced and restated later in the video, so I hope you guys can remember it without the need to take notes. The way we calculate limits are actually quite similar to the properties we use in algebra. First, let us assume that the limits of f of x and g of x at the point x equals c are respectively L and M. L, M, C, K are all real numbers and K is a constant. First, you have the sum rule, which states that the limit of the sum of two functions at a point equals the sum of the two individual limits. Then there's the difference rule, which states that the difference of them equals the difference of the two individual limits. Same for product rule, which suggests that the limit of the product of the functions equals the product of the individual limits. The constant multiple rule suggests that a function multiplied by a constant has a limit that is same as the original limit multiplied by the same constant. This rule is used extremely often, so pay attention. Then there's the quotient rule, which states that the limit of the quotient of the functions is the same as the quotient of the limits. Then the power rule states that the power of a function has the limit the same as the power of the original limit, as long as s isn't 0 and L is larger than 0 when s is an even number. Overall, this rule says that whatever operation you do to the function, you do the same operation to the limits. It is a rule similar to algebra and is actually pretty easy. Now let's see a more interesting property of the limits, that is, the limits of polynomial and rational functions. This property has to do with the definition of continuity, so we will look at this a little bit later, but please keep that in mind as of now. As we can see, as long as a function is a polynomial and rational function, which will inevitably look like this, then the limit of the function at a point equals the function's value at this point. We will look at this again later. Now, let's visit some of the places that we need to use the idea of limits. One of the things we need to get is the instantaneous rate of change, which is often just referred to as speed. We know that the average rate of change is calculated using an interval delta t of various size. Value of delta t refers to the size of the time interval, and for an instantaneous rate of change, the time interval would be instantaneous, which will be infinitely close to 0. Therefore, we get the idea that the instantaneous rate of change equals the limit of the average rate of change when delta t approaches 0. It's quite easy to understand, isn't it? Now, let's look at a more graphical representation of the instantaneous rate of change, that is, a function's slope at a certain point. We know that we have an equation to calculate the slope of a certain interval of the function, which would involve delta x. A point is an interval where delta x infinitely approaches 0. Therefore, a function's slope at a point is the limit of the slope of the interval when delta x approaches 0, which is also the slope of the tangent line of the function at a point. If you divide -1 by this, you will get the function's normal line slope at the point. Now that we've seen how to use the limits, let's get back to the dinosaur problem. We don't need to count how many dinosaurs there are at amount 10 because it's 0. We want to see what number the dinosaur counts approaching before the meteor is about to hit. We look for what the limit of the function is when x approaches 10. And wait, from the left side, the function is approaching 11, but from the right side, the function is approaching 0. So what is it actually? It turns out that some points have different limits from two sides. When we look from the left hand of the function, the limit of the function, the value of the function is approaching 11. This is the left-hand limit of the function. But if we look from the right side, the function's value is approaching 0 as x approaching 10. Therefore, this is the right-hand limit of the function. If a point's right-hand and left-hand limits are different, it does not have a defined two-sided limit. However, since we're only looking for how the value is approaching before the meteor hits, we only need the left-hand limit, which is 11. So here you have it. We have found how many dinosaurs were killed through the use of limits. Now we can also find a function's limit when x approaches negative or positive infinity. Even though infinity is not actually a number, this limit represents how the function's value approaches when it extends infinitely in one direction. For example, on this inverse function, you can see that the value of y approaches 0 as the graph extends in both directions. So we can see the limit of the function when x approaches infinity is 0. This could be represented with a dotted line that we could call asymptote. This asymptote is the horizontal one. The vertical asymptote of a function is when the limit of the function approaches positive or negative infinity. And since infinity is not a number, it will be undefined. The properties of the limit approaching infinity is virtually the same as the properties of limits in general. You can pause if you want to take notes, which will be a good chance to remind you of the general properties of the limits. With this in mind, let's now look at the end behavior model. The end behavior model is a model function used to describe a function's behavior near the end more conveniently. From the graph, we can see that the two functions have the same limit as x approaches positive or negative infinity. As the definition suggests, if the two functions' limit is the same as x approaches positive infinity, then they are right end behavior models of each other. The opposite goes for left end behavior models. And if the two functions have the same limits on both sides, then they are end behavior models of each other. Now that we have learned so much about the limits, let's have a practice question. Let's suppose that f of x equals x squared and g of x equals negative x squared. F of x is larger than or equal to h of x, which is larger than or equal to g of x, for x equals all real numbers. Now, what is the limit of h of x when x approaches 0? You have 5 seconds to answer. 5, 4, 3, 2, 1. You don't know how to answer it? Because I haven't taught you. In order to answer this, we need to use the squeeze theorem. The squeeze theorem proposes that if g of x is less than or equal to h of x, which is less than or equal to f of x, for all values of x doesn't equal c. If limit of f of x and g of x at x equals c is equal to L, then the limit of h of x at point C must equal to L as well. Let's get a better understanding of this theorem by graphing the question that I just proposed. This is the graph of f of x and g of x. The limit of f of x and g of x are both 0 when x approaches 0. Now, because h of x is squeezed in between f and g of x, no matter how weird and bizarre and spectacular this graph of h would be, its value will always approach 0 when x approaches 0 because it has nowhere else to go. Therefore, the limit of h is 0 when x approaches 0. This is the squeeze theorem, which would be useful to get the limit of a function before we even know what a function actually is. This is the end of the limit section. I hope you memorize all of them, because otherwise the dinosaur's death would be in vain.